Welcome back again. This is Larry Benko W0QE, and this video is about modeling components in SimSmith. As can be seen in the drawing, an inductor can be modeled as a perfect inductor, as an inductor in series with some fixed resistance, as an inductor in series with some frequency-dependent resistance, or modeled with a parallel capacitor, which would model the effects of a parallel resonance which exists in all inductors. Knowing when and what to model are a combination of circuit experience and common sense. The ultimate goal for most folks would be to design a circuit, simulate it, build it, measure its performance, and have the measured and simulated performances match closely. Think of this as the Holy Grail. This requires that the simulation be done with real and not ideal components, and also that the simulation includes significant new components that are the result of building the circuit. Wiring and stray capacitances are new components, as are your RF measurement skills. Previous videos that I have done touch on some of these points, and if you're not real comfortable with navigating in YouTube, here's my YouTube page. You can click on the arrows at the end of these categories and see all the files. You can also click up here in videos. And if you click up here in videos, you get a complete list of every video I've done from the very beginning up till now. And previous videos that I have done that are applicable to this video are number 5, which is RF wiring compensation, number 6, vector network calculations with SimSmith, and number 18, which is making accurate RF measurements. But at any time, you can look at them in any order. Most of the videos were intended to be looked at pretty much in any order, with the exception that I was hoping that most people who were new to the channel would look at the group that's in the basic series first. I touch on things that I consider to be pretty rudimentary and everybody should know. And the later topics aren't necessarily appealing or of interest to a lot of people. Another thing that we can do is make use of resources that are particularly good to help us estimate what our components may look like. There's a really good inductance calculator on hamwaves.com/antennas/inductance, where you design a coil. Here I've designed a roughly 1 microhenry coil, 20 millimeter diameter, mean diameter, 10 turns, 24 millimeters in length, 2 millimeter wire, which is roughly number 12 gauge wire. And I've come up with it being you also tell it what frequency you want too. I said 30 megahertz. And it comes up as a 1.03 microhenry inductor, but it measures as a 1.44 microhenry inductor, and that's due to the slight inductance increase you see due to the resonant circuit, even though the resonance occurs at 177 megahertz. But it provides things like the parallel capacitance you could put into SimSmith to model the inductance well. The other thing is any of the numerous calculators that are out there, like this one on EEWeb, which if you have wiring in your circuit that you need to include in your simulation, this is a piece of 12 gauge wire, 0.081 inch in diameter. I know I'm going back and forth between millimeters and inches. I kind of wish we'd go to millimeters and centimeters and stuff only, but we won't probably ever in my lifetime. But roughly 2 millimeter diameter wire, roughly 100 millimeters long, 92 nanohenries. This 92 nanohenry piece of wire represents not an unreasonable length of wire between components in a high-powered antenna tuner. And it's 92.4 nanohenries of uncompensated for inductance. That may or may not matter in our circuit. But little things like this allow us to put these components into SimSmith in an attempt to get what we build and what we simulate to match better. And just to finish this off, let's take that 92 nanohenry piece of wire and plot it. And here's what we see plotting from 1 to 100 megahertz on a Smith chart. I've made comments in the past about wiring also looking like a transmission line, and it does. It actually looks more like a transmission line than it does a raw inductance because of the fact that the the return current, and when you build a circuit, will try to come back on the path of least impedance, and that path is always tries to be close to the conductor where the outgoing current is. And let's see if we can make a transformer here be the same as we. Let me get this set up. This was a piece of wire. It was 4 inches long, so it'd be a transmission line. It's going to be air core transmission line, so it's got a velocity factor of about 0.95. Probably does not have much loss at all. It's 0.33 feet long since it's 4 inches. And we have to give it a new impedance, something higher because it's. And let's see where we are here. We get something like that. Is the loss that's doing it to us, or is it just we're not going to get any closer than that? We may not get any closer than that. More loss in the circuit's just going to hurt us. It's pretty much lossless for a piece of 12 gauge wire. But this is a pretty, maybe it's a little bit lower than that. Maybe it's something like in that. That's a pretty good estimation. So I don't know if this is the worst estimation for the wire or this is the worst estimation for the wire, but these kind of numbers between 150 and about 300 ohms is what you generally see. And the fact that this was done for a wire out in the open, you'll be on the high end of that. Now the downside of trying to simulate something with a piece of wire is that if we were to scan for over a higher frequency range, watch what happens here. Clearly, the transmission line starts to see a rotation, which we would expect to see, but the inductance is only going to go to here and stop. That's all it can do. It can't cross over. So this is probably a better representation to put something like this in your circuit. But anyways, these are small details, and either one of these two circuits from over the range up to 100 megahertz were incredibly close. And considering that the outcome is matching these two types of impedances. Now this was against 50 ohms here. I could do this again against 0 ohms, and we'd see that maybe I didn't quite get the right impedance then. Okay, it's 260 ohm piece of transmission line, but we can see that both of these are a heck of a lot better than doing nothing. So what can SimSmith do to help us be able to model components a little more realistically? I've made a list of things that SimSmith does that are available to us with, in parentheses, some red numbers that are my estimates as to how hard they are to do. And let's start at the beginning. And I'll bring over a copy of SimSmith here. If I take SimSmith and I put a capacitor in my circuit, it comes in with a reactance of 50 ohms. You can change this value. We can change this to anything we want. We can get 1,000 picofarads, say. But it comes in with a Q and a frequency. And that's what I want to talk about. These are things we can change. The way SimSmith initially comes in, this 2000 is a preference up here under File Preferences. It's 2000 right there. And we have, with two parameters, we have a couple of choices. The first choice, which is the default for SimSmith, is a Q, 200 for inductor, 2000 for a capacitor, nominally unless you change it. And the frequency is set at 0. 0 means it's constant frequency. So it's constant Q versus frequency. This is the SimSmith default, and it costs us nothing to do. And the beauty of it is it will make SimSmith match circuits like, or programs like LC and some other circuits, which are fairly simple in their use of loss like Q. And they work very, and maybe a very good representation of what your components are, particularly for a narrowband application, where you would put the Q in at the frequency you intended to be doing the design at and be done with it. Then we can go where we put a different Q in there. We can specify a Q. Anytime you want, you could put, for your inductor, you could set a Q of 222. A Q of 222 with the frequency being 0 would be a constant Q of 222 versus frequency. But if we make the Q of 222 at, say, 10 megahertz here, put a 10 in here, then that Q is 222 at 10 megahertz. Now the ESR, the resistive piece of the Q, changes as the square root of frequency. So if you double the frequency, the series resistance goes up by the square root of 2. As I indicated in a previous video, that was pretty much what that little capacitor did, and that's pretty much what most components do. The inductance or the capacitance remains constant with frequency, and the inductive reactance changes proportional to frequency, which you'd expect it to, and if it's a capacitor, the capacitive reactance changes proportional to 1 over frequency, which is what you would expect it to do. The result here is the Q varies with frequency. For an inductor, it varies slightly. The Q increases slightly because X sub L is increasing faster than the ESR. And for a capacitor, it decreases quite significantly because both a decrease in capacitive reactance and an increase in ESR both go to reduce Q. But nevertheless, this is a better model for most things. And it doesn't cost us very much effort to put a Q and a frequency in here if we have an idea what they are. Then we can go on here to leaving the Q field blank or putting a 0 in it. If we do that, the megahertz still works the same way the field does. It means either we start with a Q of 1,000,000 and we remain constant if it's a 0 here, or a Q of 1,000,000 and it varies with the ESR increasing as the square root of frequency. But it's a Q of 1,000,000, and this is SimSmith's version of an ideal component. And why 1,000,000 was picked as a Q, I don't know, but it's an awfully high number, not representative of anything that's real. Again, using something like that is very low effort, and it has the advantage that if you want to compare something in the textbook that you have to SimSmith, the textbook will generally be using ideal components. If you really want to be critical in a circuit, you can actually increase Qs above 1,000,000 by putting a field in the Q field here, a value in the Q field of larger than 1,000,000. I've put values up to 1 times 10 to the 9th, which is 1 billion, which is, again, way beyond unreasonable. But it lets you look at circuits. If you want to understand how the mathematics work in a circuit, you can do that. So these are the simple things you can do and in SimSmith as it exists. If we want to model the effect of the first resonance, which in the case of an inductor, it's a parallel resonance, or in the case of a capacitor, it's a series resonance, we can use either the LC component, bring SimSmith back here again, get rid of that component, and here is a parallel LC component. We have the ability to put the Q of both the inductor and the capacitor in there, and we can set our inductance to be whatever we want, and we set some small capacitance here to give us a resonant frequency, which is where our inductor will be resonant. If we do that, we can use this as our new model for an inductor. Likewise, we can do the same circuit for we can use a circuit like this for a capacitor, where this is the primary capacitance and this is a small amount of series inductance. And again, adjust the Qs and stuff as appropriate. Now, that's a fairly simple thing to do too. This is valuable to do if we want to build some kind of a wide band filter. When I say wide band, I don't mean wide passband filter, but a low-pass filter that, say you wanted to build a 10 meter low-pass filter and you wanted to stop the harmonics. You got a harmonic at 2 times 10 meters and 3 times and 4 times and 5 times. Pretty soon you're up there to where the resonant frequency of the inductors you use is you're very close to the resonant frequency. And it's very important to include the effects of that in that design of that filter then. Likewise, we can use a ruse block to do any of these things we want here. Works just fine. Components in a ruse block have the same parameters as the lumped components do. You can mathematically change them. You can do whatever you want to do. And both of those represent really good uses of SimSmith to model better something that we're going to use over a wide frequency range. The ruse circuit can be made as complicated as you want to. And if you do that, the complexity grows astronomically. and probably is not suited for most people. And if you're doing this kind of stuff, you might want to consider why you're doing it, because you're never going to get the simulation to match reality exactly. And the goal is to get most of the way there easily, and after that, live with small changes. The final way we can do it is we have a file input. Any component, not any component, but there are components in SimSmith, such as a resistor here, which can have a file attached to them. If I load a file, and this file is something like, there's one right there. I have data at various frequency points that are R plus JX or R minus JX, whichever way, if this is a negative number, of the component. That exactly could be an inductor. Now, if we use this, we have to be careful that we got a warning down here. And we got a warning down here, I suspect, because the range at which this file had data in it was 2.5 to 40 megahertz, and I scanned from 1 to 100. So if I change this and scan from 2.5 to 40 megahertz, the warning goes away. But this can be a very useful way to accurately model what I would consider to be an abnormal component. An abnormal component, a good example of that would be something like a common mode choke, which is a lot of turns wound on fairly lossy core a lot of times. It can be lower Q components. A good example would be a ferrite bead. A ferrite bead is extremely hard to model mathematically. Somebody will give you a spec for it. You could manually put the values in here if you wanted to make this file yourself. It's not very hard. It's just frequency data, comma, R, comma, X, and line after line after line with new frequency data. This can be incredibly complicated if you want to make it very, very accurate, though. But you can take a small VNA and just scan the component. I've done that numerous times, and that gives you a very, very accurate representation for a particular component. So there's a group of ways that we can do things that will improve our simulation within SimSmith. And to finish this off, let me make SimSmith show us what it's doing as opposed to what I was telling you SimSmith does. And that's the ultimate proof of what's really going on. What I have here is I have two circuits, L1 and L2. L2 is a little more complicated circuit. It's a real inductor, more real than this one is. This is the standard inductor we get in SimSmith. And let's set it to be the default inductor. The default inductor is a Q of 200 and at 0 megahertz, which means it's a flat Q over frequency. Now we can look at what we plot here. And what I'm doing is I'm taking advantage of a feature in SimSmith at the right-hand side of each one of the circuit blocks. I can look at things. I can look at voltage, current, impedance. Well, I'm going to look at impedance. L1.Z is the impedance looking from here to the left. It's a complex number. If I take the real part of that complex number, that's the resistive piece of this circuit. And there's 0 ohms in the load, so it's just the resistive piece of L1 here. If I take the imaginary part of it, it's just the reactive piece of it. If I take the magnitude of it, it's the magnitude of the total impedance. And it's pretty simple. It's telling us what, and then I do Q. Q is the absolute value, in case it's capacitive, of the imaginary piece, which is the reactance, divided by the resistance. And Q is X over R. And I do it again for the component number 2. And this really isn't intended to be a treatise on how plotting is done. I've done some stuff on plotting in the past. It's never been very well viewed, so I get the feeling that people don't either appreciate it or don't think it's valuable, or they think it's too complicated. But it is a very, very powerful piece of SimSmith, and it's part of the piece that allows you to get some things like voltages and currents on all the parts, which most SimSmith programs are unable to do. So let's look at this component right here. It has an inductance of, the microhenries and ohms is on the microhenry, and R is on this side, and on this side over here is impedance or Q. The way I chose to plot those things. 1 microhenry constant inductance of from 1 to 100 megahertz. Look at the Q. Q of 200 from 1 to 1 to 100 megahertz. Exactly as I said before, it's constant Q over frequency. Now, what does this mean? This manifests itself in a pretty simple way, and that is the impedance of the circuit, or you can think of this as the reactance or the impedance. It doesn't matter, because with Q being 100 or 200, the two numbers are virtually identical. And a resistive piece. So we look at and they're on different scales, of course. So if we look at the piece here, the reactive piece, we see a value somewhere around 62.8 ohms. We see the resistive piece is 0.31. 62 divided by 0.31 is 200. There's our Q of 200. If we double in frequency, we see a doubling. Now, this is on a log scale. Let me make it linear. We double in frequency. We see that the reactance or the impedance goes up by linearly. We see the resistance going up linearly with frequency, and they both track so that the Q stays constant. And while we talked about the fact that the resistance is rising faster than it probably should, it's hard to say for sure how fast resistance rises. The resistance term here is lumped between the actual resistance or the actual impedance of the wiring and stuff in the circuit to get from the pad on the part into the circuit, etc. But it also includes the loss in a core material if it was an inductor. It also includes the dielectric loss in a capacitor. But it generally is not that great, and so that this is too aggressive of a rise. So if we go here and we put, say, something like 10 megahertz in our frequency field, and 10 megahertz has moved down here now since I went to a linear scale on frequency. What we see is constant 1 microhenry inductance still. We see the reactance or the impedance rising linearly, which you'd expect it to because it's 2 pi FL. And we see the resistive piece rising as a square root of frequency. It does not rise nearly as fast. It rose to 3 ohms or a little bit more in the previous example. It only rises to a little bit over an ohm here. And if we look at this closely, we see 0.31 ohms at 10 megahertz. If we go to 40 megahertz, we should see 0.62. And we do. So it's rising as a square root of frequency. That means that the Q is rising also. And this is more typically correct for an inductor. Now, an inductor may be out to some point like this. At some point, the parallel resonance piece of this starts to kick in and destroy the inductance. But nevertheless, this is a better model than that model is for an inductor. This, again, like I said before, matches other programs nicely. And it doesn't, if you put a number in here in SimSmith would have no idea what number to put in here. Classic numbers to put in here are 790 kilohertz, 2.52 megahertz, 7.9 megahertz, and 25.2 megahertz. And the reason being that those were the frequencies that the old HPQ meter used to read Q directly out on the dial. I mean, that, as stupid as that may sound, you still see those frequencies used all the time for small inductors. And if I wanted to use this at 10 megahertz, but I had the spec at 7.9 megahertz, I'd put 7.9 megahertz in here, and the spec that the manufacturer gave me for the part, and I could use that, and that would be a better model than probably anything else short of measuring it. So now let's look at a real inductor. Let me close everything off here so as to not be too much stuff at one time. The real inductor is going to be that exact same inductor I just did over here, and it's Q of 200, 10 megahertz. It's going to be in parallel with 5 picofarads. Now, 5 picofarads is a lot of capacitance. Real capacitance is probably a little bit less than that, but I wanted to get the resonant frequency down below 100 megahertz just for the example here. So it's 5 picofarad capacitor. I gave it an infinite Q. If it's an air-wound coil, the capacitance has got a pretty high Q. I don't know what it is. It really doesn't affect things a lot. So let's look at what this component does as a lumped component. The first component, L1, had constant inductance versus frequency. L2 starts off as 1 microhenry, but it starts to rise. As we saw in our example on that inductor previously, there was a slight increase in inductance due to the capacitance. Now, if the capacitance, this resonant frequency, I believe, is like 71. It's 71.2 megahertz or something like that. If we go to say 1/3 of that, so 71 divided by 3, say is about 23, 24 megahertz. Our error here is about 12% in inductance. A 1 microhenry inductor that's marked on the inductor at 1/3 of the resonant frequency will be 12% higher. If we go to half the resonant frequency, which is about 36 megahertz, we see it's about 30% high. Now, in some circuits, you may not care about that. In other circuits, like a filter, you care a lot. That's why it's important to include this in a wider band filter. Let's keep going while we're doing this. We look at the Q of our first circuit, and what we see is we see the Q rise. The Q rises as the square root of F because the reactance is rising as F, but the divisor is rising as the square root of F. So the net effect is we're rising as the square root of F. We look at the Q on the circuit with the capacitor, or the included capacitance, and what we see is it rises just like the original one does, but it starts to fall off. And clearly the Q goes to 0 at resonance. And then back up again here. This is why I had the absolute value in there, because this over here on this part right here, this inductor actually is capacitive. And this is kind of an interesting thing. So what we get here, and I've heard people say things. When I was a kid, I read an article one time where this guy was touting how this worked, and I had no idea how you could ever increase inductance by adding a capacitor in parallel with it. And he was making a comment that this was basically some kind of free lunch. And a free lunch being he couldn't get an inductor of large enough value, so he nearly resonated it, used the circuit slightly below the resonant frequency, and he was able to get this higher inductance. Well, he was able to get a higher inductance, but it was at a lossier component. And as pretty much everybody who's been around the block more than once or twice should know, free lunches generally are not they're not quite what they're cracked up to be. So what we see here is we see if I wanted this 1 microhenry inductor to be a 3 microhenry inductor right up here, my Q now on that inductor would be, let's see so I can get there, it'd be right. My Q would have dropped now to 161. Now that may be okay, you may not care, but that's 161 versus 481 for the part if you had built it so that the resonant frequency was way up there, way higher in frequency than the 70 megahertz. So it's something you have to be careful about. But SimSmith tells us a lot of little things like this. So if you were sitting in front of SimSmith some night and you had nothing to do and you start playing around with things like this, you get to where you start to understand things that you've read in the past. Things that were read in the past by people who touted these things as being obvious, but never really proved them. Never showed what they really were. They just said them. And some of these things you can take at face value, and they're true all the time. Other things you can't really, there's particular caveats and stuff where it's true only in certain conditions and not true in others. But SimSmith is a wonderful judge to be able to discern whether or not something's really true, really false, or what's really going on, particularly in a circuit. But it's all based on the fact of your ability to model it accurately. Anyways, hope you've liked this video. If you have, please click on the like button. And if you know people who would like these types of videos, please refer them to this channel. Thank you very much.